Hello, Assalamualaikum, and very good day to everyone. Today, our lecture is to how to design shear link for the beam. Shear design is one of the ultimate limit state, which is we design it to avoid the collapse of the building. Remember, in the analysis of structure, we have a moment and also we have a shear diagram. So in this design, we will design the shear link to resist the shear force that we obtain from the analysis. So in the design, Eurocode suggested that the shear force can be resisted by using vertical shear link or stirrups. This figure shows the arrangement of the vertical link stirrup in a cantilever beam. It can be seen that the stirrup is spaced closely between them near to the support. Again, this picture shows the arrangement of shear link in a beam in a building. Well, before we proceed to the design of shear link, we must understand theoretically the development of shear force in the beam. This beam shows diagonal crack due to the shear failure near to the support. The diagonal crack developed underneath the load directed to the support. By using this diagonal cracking, EC2 uses this as a basis for the derivation of the design for the link. According to the EC, the beam can be modeled as a strut inclination method, such as shown in the picture. The transfer of shear force in the concrete beam is just like a transfer of load in a strut of the truss. The analogy of the strut inclination is shown in a figure, which is shown that the vertical link is in tension, while the diagonal cracking representing the concrete in compression. In EC, the diagonal cracking representing the concrete strut is in compression, and in the design it represented by the VRD maxima and has the inclination of theta, which is in a range of 22 degrees to 45 degrees. This VRD maximum is a force in compression and will be balanced by the VED by the vertical shear from the reinforcement VRDS. The horizontal component of VRD max will be balanced by the force due to the flexural reinforcement or delta FTD. Determination of VRD max is shown in the equation 1, which is design stress times the area. Design stress here is from the concrete strength, design concrete strength, times with the area of the concrete in compression, that is BW times Z cos theta, and times sine theta. The reduction factor for the strength and also for the state of the stress in compression chord will be introduced in the VRD max, and it become a new equation VRD max, such as shown in equation 2. Further, the equation for the VRD max is simplified and shown in equation 3 as recommended by EC2. shear resistance from the link is given by the VRDS, and it's equal with the FYWD is the stress in the link times area of the link. Area here is the area of the leg of the shear link. Question 5 is the force in the link that taking into account the spacing of the link and will be used throughout the design of the shear link. So for the design of the shear link, VED or the applied shear force that is obtained from the analysis will be equal to the VRDS or force from the shear link. So we can get the final equation of ASW over S equal VED divided by 0.7 FYK d cot theta, such as shown in equation 6. Again, remember the ASW is the area of the two legs. If we refer to the figure, it is two legs. So the area of the two reinforcement. And here, the important that we design is the spacing of the link. And this spacing must not exceed 0.5D. Eurocode also provide that minimum link beside the vertical link. So equation 7 must be used to obtain the minimum link. Again, the ASW must be selected or assumed, and S, we determine the S and it must not exceed 0.75D. So in this picture, you can understand that vertical shear link is located near to the support, while the minimum link is placed near to the middle of the span, if in the case of simply supported. Another thing is that minimum link, usually we assume that the theta is 22 degrees, while vertical link, we need to calculate the theta. It must not exceed 45 degrees. Therefore, we have the step for the design procedure for the link. The first one is determine the shear at the support, VED. And the second step is to determine the value of the concrete strut capacity or VRD max for the inclination strut of 22 degrees to 45 degrees. So you need to calculate both of them. Step 3 is we need to compare with the VRD max theta, cot theta 1.0 or theta 45 degrees. So if your VED greater than this value, meaning that you need to redesign the section, meaning that you need to change the H of the beam. Step number 4 is for if your VED less than VRD max when cot theta is 2.5 or when the theta of the strut inclination is 22 degrees. So in this case, you need to calculate the vertical shear link using the following equations. Then we need to calculate minimum link at step 6. For the step 5, this is the case where your shear force from the analysis is in between the value of VRD max cot theta 22 degrees and less than VRD max when the theta is 45 degrees. So in this case, we need to find the actual theta using the equation given and followed by the S or spacing of the vertical link that we required. And last step we also need to calculate or find minimum length. The step 6 is the equation for the calculation of the distance or spacing of the minimum length. Usually ASW will be similar or the same value with the vertical length. And step 7 is the calculation of additional longitudinal force, delta FTD. Delta FTD is the force which resists the concrete strut in horizontal component. So meaning that this is to check whether the flexural steel are sufficient to resist the delta FTD. This diagram shows you briefly how to design the shear link from the start to the end, step by step. So let's see the example of the design of the vertical shear link for the simply spotted beam with length 7.50 with the design action 58.22. So we need to find what is the shear force. This is simply spotted beam, so only sustain the uniformly distributed load. So the shear force can be calculated by using this formula, WL over 2. So we have VED is equal to 108.3. So the reaction here is called VED. The most important thing, the information here is the FYW given is 250 Newton per meter square. This means that the shear stress in the link is 250, not 500. Okay, for the solution, the first step is to identify, we have identified the VED, that is 218.2 kilonewton. Therefore, we need to compare our VED with the concrete strut capacity VRD max. So by using the equation given and the data given, you need to calculate the VRD max for two strut inclination, that is 22 degrees, or cot theta 2.5, and theta 45 degrees, or cot theta 1.0. So you need to calculate two times. First is by using cot theta 2.5. Just insert 2.5 replacing cot theta in this equation, and you will get two values. So we need to compare it, VED, whether VED is in between or less than both value. So in this case, VED is less than both value and less than the lowest value, which means that the theta we use in design is 22 degrees. After we obtain the VED and compare the VRD, now we have known that we need only shear link with this equation, ASV divided by S, VED divided by 0.78 FI with D cot theta. And by using this equation and replacing theta as 2.5 or 2.48 here, it round up to 10.5, meaning that the theta is 22 degrees. So we have ASW over S 1.085. Remember that we don't need to calculate, we only need to calculate ASW over S. And then the next step is that we just try link R8. You can use other diameter. Usually diameter of the link is 6, 8, 10, and 12. So let's say we want to try R8. It's up to you. So here we try R8 with ASW is equal 0.57. This area is actually two area of the R10, diameter 10. You can see from the appendix two area of diameter 10, which means that we use two leg. So from here we can get S145. And remember, this is the spacing for the vertical shear link, and it should be compared with the maximum spacing allowable 0.75D. Therefore, the vertical link here is R10 with the spacing 1 to 5. You can see here R10, R means mile steel. So if it's mile steel, so FYV is equal to 50, not 500. You can see why we choose 1 to 5 is because 1 to 5 is less than 145. 145 is difficult to measure in a construction site. So usually we will round up with 25 millimeter. So therefore we choose 1 to 5. The minimum length we calculate using the formula given, and again usually we will use the same diameter as the shear link, that is R10. R is because of mild steel with the strength of steel is 250. So we get new spacing for the minimum length is 359. Again, this spacing must be less than 0.5D. So here the spacing of the minimum length is greater than 0.5D. Therefore, the selected minimum length must be based on the maximum spacing 313. Therefore, we use R10 300. We have already designed the spacing for the vertical link and also the minimum link. So the problem now is how to arrange the link and what is the distance required for the total distance required by the vertical link. So therefore, we need to find Vmin. Vmin is the distance. By determining the Vmin, we can get the distance where the minimum link starts. Vn can be calculated by using the formula for the vertical link, with theta is for 22 degrees. This is the starting or the force that given by the minimum link. By putting the Vmin into the diagram of shear force, now we can get the value of X. X means the spacing that requires vertical link. To get X, you can use the formula given in the diagram or simply by using the interpolation, the similar triangle diagram. After you have calculated the X, now you can get the distance, where the location of the minimum link as shown in the diagram. Finally, we need to calculate the tensile force or the flexural reinforcement needed to counter the concrete strut in the horizontal component. By using the formula given, delta FTD is equal 0.5 VED cot theta. The theta here must be 25 degree because our vertical link, the theta we obtained above is 22 degrees. And the additional tensile force we obtained must be compared with the uh, force obtained from the moment divided by the module sections. So in this calculation, the delta FTD is much less than the moment divided by Z. Consequently, we can calculate the area of the steel required by dividing delta FTD divided by the stress of the steel. So we can get 6 to 1 millimeter square. Or we can obtain the area of steel and the number of steel at the appendix, and it is 2H25, meaning that at the support at least 2H25 must be provided. Finally, the detailing of the link and also flexural steel must be shown in the detailed drawing. You can see here that the arrangement of the flexural steel, which is at the midsection, it has a 6H25, while it can be cut it at the support and let at least two numbers of steel extended to the support to resist the shear that we calculated just now. And also in the picture, you must show the arrangement of the position of the vertical link and nominal and minimum link. And not to forget, the link must also be shown in the cross section XX.